Okay, the brief introduction is the following. First, I will say a few words about torsion. After, I will show you experimental procedure and materials, results of very high cycle fatigue test on pure torsion, some details about the model, and result of numerical simulation. I will try to be quite short too. So it's very important to perform some very high cycle fatigue test in torsion. You know, even for car industry, right now we have a very long fatigue life, about 10⁸ cycles. If we considering another application, something like aerospace application, so we'll go to 10⁻10 or even 10⁻11 number of cycles. So, and every time you have some rotation for blades, for other applications. So torsion is very important subject for experimental investigation. So here you have a set for torsional test. Right now we use a direct pure torsional system presented on the slide. So, and we are sure that our loading condition good, because we are still working at low temperature, constant amplitude loading, and we can perform perfect calibration with a strain gauge presented on the right. So, and based on the procedure that we developed for torsion test, we perform very high cycle fatigue test at 20 kHz in pure torsion for titanium alloy. The details of titanium alloy is presented here. So, and it's very interesting to test this material because it has not some non-metallical inclusion. So, for example, the first results for steels show that sometimes we have subsurface crack initiation with the inclusion. Here, in case of the titanium alloy, we don't have an inclusion and still have different types of crack. Here, I present you briefly the results of experimental test on material. So here on the right, you have a push-pull test on the same titanium alloy. It's an axial test, and we use the equivalent stress to calculate the results of torsional test here. You see torsional. So they are pretty good, match each other. And if we have a look on the lateral surface of the specimen, we have normally two types of crack. Sometimes we observe that just a single main crack lying in the plane of 45 degrees. Sometimes we have a double crack here, so that similar to the X shape. And we was trying to investigate what is the difference in the spatial shape of the crack, depending on the mechanism of crack initiation. Here you have a little bit more details of the crack growth, and we have to pay attention that during the initial state, we have a small part where a crack is growing in the plane of maximum shear stress. So it means that at the initial state, we have a pure shear as a driving mechanism for crack opening. If we have a look on the fracture surface, we can see that there are two types of cracks. The first crack is starting from surface, and we call it surface crack initiation. On the left, you see it's quite similar to the classical high cycle fatigue with a manufacturer roof morphology. And the second type of crack under the very high cycle fatigue torsion loading is a subsurface crack initiation. When we observed the crack initiation seat, we did not find any non-metallical inclusions. So it's just a feature of microstructure leading to the subsurface crack initiation. And as you can see, it's far from surface. It's about 600 microns from subsurface. So it's quite unusual because the maximum torsional shear stress are acting at the surface here. So, and in this case, we have two cracks, one developing in the plane of one orientation and second one perpendicularly starting from surface. So, and when we have a subsurface crack initiation, usually we observe X type of cracks. So, and in order to better understanding this phenomena, we try to apply the numerical simulation and try to modulate the crack with a different crack initiation seas. Here are some details about the models that we use. We use a idea of the full SN curve with the left and right branch. Right branch is relating to very high cycle fatigue. Left branch, we relate to the classical mechanism mainly for high cycle fatigue because we're always working at a relatively low stress amplitude here. So, and in this case, we extend our knowledge about the high cycle fatigue to very high cycle fatigue. And we introduce the similarity in the shape of SN curve here. So, and we introduce the kinematic equation for damage function. It means that we describe the material locally at the local point, and we follow the degradation of material, and after link the degradation of materials that we described by damage function with a elastic moduli of material. Here we have some details about this model, and we associate that this degradation of material could be led by the normal crack opening and shear crack opening. And during our calculation, we use a double step verification. So we check the stress state with one criteria, that is a Smith-Watson-Toppler, and with another criteria, Carpentieri-Ventadori-Spagnoli, that is describing the shear crack under the tension. So, and here you have some details about numerical simulation. We use the spatial algorithm that allowing us to get the analytical solution for damage function at each time level and each point. So, and finally, we built the 3D model. We use ANSYS for calculating the stress state. We can make calculation in elastic assumption or elastic plastic. So elastic plastic is very long, and here I present just elastic solution. So we calculate the stress state with ANSYS. After we apply our algorithm to calculate the damage function, and use the kinematic equation to describe the evolution of damage. And
Alexander, I am sorry, time is short.
Okay, so, and here the green color introducing the quasi-crack. So, and we get the crack initiation from surface after we put additional hard element inside, deeper and deeper, and we got the X-type crack with the two perpendicular. So, and finally we arrive to conclusion. I can say that we observe two types of crack, surface, subsurface, and we introduce a model based on damage theory. And applying this theory, we are capable to predict some special features of crack initiation under very high cycle fatigue. That's all. I think.
Alexander, thank you.